All right, hello everyone. Let's get started at 9:10 here. So the first thing I want to do is just show you what I was, or maybe the key of the assignment that you had. Okay, so what I was asking you was starting at SOIK, so the raw data, right? To use data wrangling functions that we use in this class in a pipe workflow. So using the pipe operator to generate the average potassium concentration for each potassium rate within each location, right? So we're basically averaging over reps. So what I guess most of you already submitted the assignment on time, so thank you for that. I will get the grades out. I have already the grades. I just have to figure out how to enter them on ELC because I haven't been using ELC as much. But most of you got it right. Some of you were a little bit confused. So let me walk you through what I was expecting from this assignment. So starting with SOIK, if you really wanted to go through each one of the individual ones that we talked about in class, you could have. I was really hoping that you would use this sentence here to guide your decisions of what needed to be done to this data set, right? But really, if you understood what we did in class and if you understood the question, you could have really just copied and pasted this all the way through the arrange. Right, and if I run this, I get the full table, so not group by or summarize yet, right? So the next thing that you would have to do was to use that combo that we talked about as far as group by and summarize. So you would add a pipe. First, you had to group by. So in our class exercise, we group by location only, right? So this is what we did. However, I'm asking you here, to give me, let me go back to the sentence, to give me the average for each potassium rate within each location. So what that means is that I was really expecting you to plug in here potassium rate. Some of you got a little bit confused here, maybe because maybe my tip was actually throwing you off because some of you here put rep instead of potassium rate. But when I say here, we're averaging over reps. So if we're averaging over it, we're not having that information in the table. So here should have been potassium rate. So if you do this, and then you summarize, just get the mean, okay, PCT. This is what I was expecting for you to turn in, right? So most of you did this. For those of you who didn't, you lost some points just because you used the wrong grouping variable. But that was kind of that this is the key of what I was expecting. So what I was looking at is if you had first 16 rows, if you had the proper columns, so if you had location and if you had potassium rate, so some of you had treatment or perhaps rep here. And then if your means were calculated properly. Of course, if you did have the grouping correct, your means should have been correct as well. And if you had a different variable here, perhaps your means were not correct. But anyways, this is the key. This is what I was expecting from you. And as you can see, it was really a very small tweak on what we did in class. It was just adding an extra variable on the group by, and that variable, should have been potassium rate as the instructions of the assignment tried to make it clear. Is it clear for everyone, especially like if you missed it? Anyone has any questions about it? Okay, I don't hear anything, so I'm gonna take that as everyone understood. Let's just keep going. So today I actually is one of the few classes that I am gonna have some slides for you. And I just want to tell you again, so every time I have slides, they're going to be on my website, on the course website. So if you go there, and I hope that by now already have this bookmarked somewhere. But if you go to my website, it's going to be that the class for today, there's going to be a link for slides. I'm just going to open that here. And just to remind you as well, if you do want to take notes, if you have this open, this is HTML, but if you push E on your keyboard, it kind of makes it like a rolling file instead like a presentation that incrementally appears. So if you push E on your keyboard and you go on File, Print, you can save this as PDF and take notes on your computer if you want to. Okay. So today, we're going to start talking about geospatial data and some of the differences. So on the survey that you all responded in the beginning, I could get a feeling for, how much exposure and experience you all had with vector, raster, the difference. That's going to be really important for us moving forward in this class. So I just want to touch base on that again, talk about coordinate reference systems. We're going to be using mainly two types in this class, but there are, I don't know, thousands of them out there. So I really wanted to make this point. And also then talk about NASS. So NASS, well, it's a USDA data set that we're going to talk about in a second here. Yes.
You can send us PDF.
Yeah, so to save as PDF, let me just escape here. So you push E on your keyboard, and that makes it like a rolling type of file. And then if you just go on your browser, on your, on Mac's is File and Print. And then at least on the Mac, it has this option here, PDF. You can save as PDF. And you can also, I know that on a Windows, it works similarly. Perhaps it's not exactly the same. But if you want to change the landscape, that's going to look better. If you want to change, let's see, how many, where was that? Maybe layout, like how many per sheet you want. You can also do that, like 2 or so. Yeah, but then you just save as PDF somewhere on that print window. Okay, so let's talk first about some geospatial data types. So really, as long as we're going to be working in this class, we're going to have two main types of geospatial data. The first one's going to be vector. The second one's going to be raster. So vector formats are, if you heard about them, you probably heard about the term shapefile. So shapefile is one format that vector data can come as, but there are different ones, right? So if you ever use shapefiles, the reason why we call these shapefiles is basically because Esri, the company that was the pioneer in this area, that's the name they gave, and it kind of, stuck with the concept. But really a shapefile, if you think about it, is really a type of file that is normally a SHP type of file. And also, if you've ever worked with shapefiles, you know that if you only send me an SHP file, that will not work for me. You have to send me all the accompanying files that come with that, so I can really use that later on my site, right? So normally, like ranging from 3 to 5 accompanying files that need to go along with the SHP for me to be able to open the shapefile that you send me on my site. There are some other types of shapefile or vector formats. So GeoJSON is one that we're going to be using in this class. It is kind of similar to a shapefile. I mean, it isn't behind the scenes, it is indexed differently. And one of the things that helps us is that is actually just one file. So if you send me one, let's say field boundary.geojson, that is the file I need only. If you send me a shapefile, I had to send me 5 or 6 files that are all related, so I can use that on my site. And also, if you've ever used, Google products as far as like Google Earth Pro or others, Google uses KML and KMZ, which are also vector formats as well. So a vector type of data is really, it can be a point, a line, a polygon, or even a mixture of these, right? So normally in agriculture, if you think about it, a point data is very common if you are, so if you have geomonitor data, that is point data. If you're going out and doing soil grid sampling, that's going to be point data. Anything that you go to a place and you take a sample and you want to know where that sample is, that's going to be a point data if you're using GPS for that. A line string is basically, it's just a line. But the main difference between a line and a polygon is that the line doesn't close, right? You can think of it as like if you're digitizing roads, for example, or maybe rivers, or things that are linear but never close in that shape. That's going to be a line. In ag, I think I mean, on ag field, precision ag, we don't really use line strings that much. I think it's going to be mostly points and polygons. And then polygons could be a field boundary. It could be a zone that you created, that you have a delimited zone that is a closed polygon. So these would be the types of data that would be considered a vector and that we're going to see a lot in this course. So in R, I just want to walk you through a little bit of the history of geospatial analysis in R, because as you develop your own skills, you're going to learn very quickly that Google is your best friend. And when you Google things, you kind of have to know how to Google properly, like what package to Google for, so you know that you're really finding the answers that you need. So initially for vector data in R, the main package was called SP. So it was the first to be created. It was really able to, so if you ever worked in a GIS, let's say ArcGIS or QGIS or something like that, you probably know that like you have the spatial data, right? So you would have like a polygon, let's say a field boundary, but then you also have an attribute table, which is basically where the data about that polygon is saved. So you're going to have, let's say, probably you could have things like previous crop, or maybe average yield, or whatever it is that you could have a confined boundary, and the data at that level is what you would have. Or maybe if you have, a point data where you sampled soil, that point data is going to have all the columns for the soil nutrients that you analyzed, right? So it's basically merging the spatial information with the attribute table, which is the data that comes with that spatial information. So in R, package SP was the first one to do that, to merge those two pieces of information to be used in R. However, they did it in a somewhat complicated structure. We're not really going to use much SP package or SP objects in R, but I just want to tell you why we're not using that. It's just because it's a very complicated, like the data, the attribute table data and the spatial information are kind of like combined, and it's not easy to separate them in a way that you can play nicely with graphs and analysis. And that makes it difficult to manipulate its data frame side of it. And it's also not pipeable. As we're going to see, we're going to be using the pipe a lot. So given that it's not pipeable, so it doesn't work well in a pipe workflow, is also a downside. So what will we be using actually? So the package SF, which stands for simple features, it is a newer package than SP, and basically addresses the shortcomings that I just talked about SP. And it really, one of the key things that you're going to see maybe today, maybe Monday, is that it has that spatial component there as well, but it has the data like right next to it, but separate. So you can really treat it as a data frame, even though it is a data plus geospatial information together. So it is pipeable. It works well with the wrangling functions we used. So that's why we're going to be using SF. All right, so let's switch now to raster formats. So again, the two main types, vector and raster. So raster formats are, in ag at least, most commonly what we see is a .tiff or geotiff, or something that has tiff in the name. There are some others like ASCII grids. This is also an ASRI product. There's bitmap. There's really a lot of different file extensions that can contain raster data. We're going to be seeing and using mostly TIFF types of files. If you do want a full list, this is a link. If you click here, it's going to take you to an ArcGIS page that has a very long list of raster files, in case you're interested. I don't think you're going to gain a lot from it, but if you're interested to see how many types are there. Okay, so a raster file normally is associated with some sort of imagery. So if you have UAV imagery, if you have satellite imagery, or some type of imagery, that is a raster file. So when you take a picture on your phone, that is a raster file. Or perhaps it doesn't originate with an imagery. So let's say if you go out and take grid sampling, soil grid sampling, right? So you take multiple points, and so you send them for soil test, and you know how much P, K, whatever nutrients you're interested are on that spot of the field. But what if I want to know right next to it where I didn't sample? Well, we don't know that, right? So we have to interpolate. So interpolation basically takes point data and creates an even continuous surface of that data. And that output is also a raster because now it's continuous. You have cells of a given size and it have information all across it. So that could also be a source of raster type that we're going to be using imagery. We're going to be creating interpolated maps. So we're going to be seeing, again, vector and raster in this class a lot. So here's just an example, right? So this is green NDVI maximum value over a growing season for a field. And you can really see that it's a continuous data, right? So it's not point, it's not, you don't see like, I guess, holes in this layer. It's a continuous layer, it's coming from imagery. So this would be an example of raster that we get from imagery. And this here would be an example we get of a raster from interpolation. So this is coming from an EO monitor data, which again is point data. Even though it's very dense, you have lots of points, but still point. So if you want to have a continuous coverage of that layer, we do interpolation, and the output of that is a raster file. Yeah.
Since there are a lot of points, then is it like using vector data to make the raster?
Yeah. So the question is, if you have lots of points, do we use the vector data to make raster data? That is exactly what we do when we do interpolation. There is a way that you can pretty much just like take a. Well, we're going to see this next. So let's just pin that question for a couple slides down the road because we're going to talk about exactly that. Okay, so raster data in R. Very similarly, so there are 3 different packages. I need you to know this again, because if you run into issues and you want to Google, how do I do a raster, whatever operation in R, you should be asking your question using package X, because that's going to give you the answer you're after. So with raster, there are 2 packages or 3 packages, but 2 that we're not going to be using are called raster and Terra. So raster again was the first in this area. Terra was a newer package. It's faster than Terra, but it's not pipeable. And we're going to be using, for the most part, package stars. So package stars was actually developed by the same person that developed SF. So the person that developed the good package for vector also developed another one for raster in R. And it is, again, newer than the raster package. It is pipeable. And because the same person created both, they share some concepts and functions across those 2 different packages, which makes it really handy. And this is what we're going to use for the most part. Okay, so now, Sandesh, I want to come back to your question. So if you look at something, how do you even know if that is a vector or a raster? I gave you some hints already, but I just want to show you here one way that you can go from point data to raster data, and how does that look like, and how do you know that you have one or the other, right? So here, this is an example I got from a book where we have this person went out and collected a whole bunch of points data. And the legend here is saying capacity. I don't know what capacity of what, but it's numerical. So it ranges from 0 to 50, and they have these different breakpoints. There are different colors in this map. And again, this is vector, right? We have a point data, this is vector. Now, if we were to transform this to raster, there's a couple of different ways that we could do. So one of them could be just presence absence. What does that mean? It means that everywhere there is a point, regardless of the capacity count, everywhere there is a point, you say 1. Everywhere there is not a point, you say 0 or NA. So that's pretty much what we're seeing here on this presence absence map, where now if this grid, I mean, we're not seeing the grid, but you can kind of imagine the cells here. This would be a grid cell. Everywhere in this grid cell that there was a point above, it changed to a value of 1 because there was a point there. If there was not a point, then it's basically 0 or NA. So one big difference here to notice is on a vector shapefile or on a vector data type like point, you do not have to have continuous data, meaning that if anywhere that is empty here where I don't have a point, is really nothing, there's nothing there, there's no data there. On a raster, you have to have data across all that entire bounding box. So here we're just seeing the value of 1, but wherever it's white here is basically either 0 or NA. So again, raster is continuous data. Even if you don't have data, you still have to say that there is nothing there. Vector, you can have empty pockets if you think of it like I have 0 data for there's no column or row in my data set, about these white areas on the points side of it. However, when I transform that to a raster, I do have a data there saying that this cell is empty. So that's one of the differences.
If I look like in between the points, I mean the deltas, there are spaces. But if you look on the raster, there is no spaces. I was feeling like maybe those graphs, which looks like no points, that's supposed to be empty in the raster.
So you mean like places like here?
Yeah, like those it looks like big holes with no
Right.
Here they are covered because of the interpolation.
No, so actually there was no interpolation here. What happened, and this is a great question because it could certainly be confusing. What's happening here is if you, I'm assuming just by looking at this, that this is because whenever you do interpolation or you go from vector to raster, you the user have to define a grid to give it, right, to give that conversion. So I'm assuming that when the person that did this defined a grid which cell size was this. So if you think of it, if this is the cell size, it means that even if a point was like right at that edge, but nothing else anywhere else, it was still saying as yes, presence. You know, of course, if this grid cell size was smaller, then you would have seen a lot more empty spaces where we do see empty spaces in the point shape vector. Does that make sense?
Okay, so it's like just pull the pixels together.
Yeah, I mean it's so we can think about pixel when we talk about raster, right? So this would be a pixel. So if we were to overlay these two layers, I'm confident that here there was a point at least somewhere within this pixel, right? But it means that maybe the pixels in the middle had like 10 points in one pixel, but maybe the ones on the edge here maybe only have 1 point in the pixel, right? So the pixel is just saying yes, no, there was a point here, right? So that we don't know yet how many were there. It's just like a presence absence type of conversion.
That means we can change the view size and make it more precise.
We could, yeah. So Sandesh made a good point here. So could we make the grid size, the cell size smaller? Definitely. This is something we're going to be doing in class when we do interpolation, because we're going to have to decide what is the size of the grid cell that we want to use. When we do interpolation, for example, soil pH, we go and take a whole bunch of points, but now we want a continuous raster data. We have to define the grid size when we do that. And that is somewhat arbitrary. We can use some science to define the best value using machine learning approaches. We're not going to be doing that in this class. We're going to be more, at least using an educated guess of how big that should be. But we'll get there in a few classes. Okay, great questions. So another way that we could transform this point this vector point data to a raster would be to include that count information. So you can see that now the third map here is in, at least the shape of it is the same as, so C shape is the same as B, but now we also brought that information of how many points there is, how many points fell within each one of the cells of the grid that was defined here, right? So we really see like right here, you know, these points here, which are probably somewhere here, they have like from 15 to 20 points falling within each grid cell. So that's also something you can do, and people do a lot of this when, especially working with like urban type of studies where, you know, you have some type of population measure, and it's interesting to see how many events happen according to population size. This is something that they do a lot. We don't do this type a lot in ag, but I just wanted to show you a different way of expressing or transforming from vector to raster. All right, any questions? All right, I'm gonna keep going. Okay, so we talked about vector and raster. So you can think about it again, a vector is gonna be a point, a line, or a polygon. Most in ag, we use points and polygons. So points for like when you take a sample and you georeference it, that's a point. And if you have a boundary, like a field boundary, or maybe a zone boundary, that's a polygon. And a raster would be mostly when you have an imagery or a product coming from interpolation. That you have continuous data. Even if you don't have data, you still have to have a cell saying there is no data here. In vector, that doesn't happen. If you don't have data, you just don't have that data on your data frame. So now let's talk a little bit about coordinate reference systems. I know that Dr. Lacerda talked a lot with you about this, and I just want to maybe like focus this to what we're going to be using in this course. So two main types of coordinate reference systems or general classes would be geographic versus projected. Let's just talk about that a little bit. So a geographic coordinate system is probably the most common that you've seen on your phone or even on GPS or different things that take coordinates when you're using it. Most of them are using a lat long system, right? Where one of the ways, at least that we refer to that, is just to use the WGS 84 coordinate reference system to refer to that lat long type of geospatial information. So I know that you went through this with Dr. Lacerda. We're not going to spend a lot of time here, but basically lat and long, you have a main center, right? So we have the meridian, we have the equator, and those are the main lines that we use to guide all across the globe. So we only have one reference that you're using anywhere in the world you are. You're going to be using still those same references to refer to as far as your position. So we talked about this. We have parallels of latitude and meridians of longitude, and this is, again, the most common one that you're going to see. However, with every projection or coordinate reference system, there is going to be some sort of distortion, right? There will always be. This is a trade-off. There is no perfect one. And with lat long, it's really useful like on a world scale, but if you're trying to do interpolation on your field here in Georgia, maybe that's not the most accurate or the best one to use. So what do we do then? Well, we use a projected coordinate system, and the most common one that I'm sure you're already aware is the Universal Transverse Mercator, also known as UTM, is the most commonly used. Now, UTM, differently than WGS 84, it kind of takes the world and splits it into zones, like into vertical zones. And each zone has its own reference, like center of reference. And that helps it to avoid distortions that WGS has, because WGS only has one reference, and that reference distorts things as it goes around the world. And UTM basically has multiple references, one for each zone, that helps us to make things more planar and less distorted due to the shape of the Earth. In Georgia, this is going to be important for you to know. We have two zones. So Georgia is covered by two zones, the 16 North and the 17 North. And most of Georgia is actually within the 17 North zone. So just to show you here, let me zoom in a little. So this is kind of what UTM zone numbers work for the entire world. So it's basically, you have these verticals splits starting at 1 going all the way to 60, and then a same zone. So if we look at Georgia here, we are mostly on the 17th zone. So there's a 17 North if you're in the Northern Hemisphere, there's a 17 South if you're in the Southern Hemisphere. So that also makes a difference to say that it's North or South. And while WGS 84 is just one reference system that works for the entire globe, UTM is also one, but whenever you specify which zone and hemisphere you are, that has its own projection information. So here we have basically 60 times 220 different projection informations on this, whereas WGS is one for the entire globe. And again, just to show you here, Georgia falls mostly within the 17 North UTM zone. There's a little bit of Western Georgia that falls within the zone 16. And I remember, if you had a class already with Dr. Velides, he was telling me about this time where they had a study in South Georgia where the field was actually right at that boundary. So like part of the field was within 17 North, part was with 16 North. And that was just a big hassle because you have to be, depending on what part of the field you are, you have to be using a different reference system. So that's kind of an interesting situation. I hope that most of you are not going to be with that. Your fields are either going to be in one or the other. Okay. So let me show you here, and I want to ask you something. So I have here the same area. On the left, we have it as geographic, using a geographic coordinate reference system. On the right, I have using a projected coordinate reference system. What is one difference you notice? The units, right? Yes, the units. So geographic is in degrees, right? Degrees, minutes, seconds, and so on. And that's the unit that longitude and latitude are used as. Whereas projected is not degrees, it can be meters, it can be feet, but is a measure of distance. It's not an angle anymore, right? So that is one way to know what type of data you're using, and just so you have some idea. And also, I don't even know what's the size of this. We don't have a scale on this map, so I don't know if this is a state or if this is a field or if whatever this is. But and perhaps it's not very easy to see here, but there are differences in how these, if you were to make two maps, one in WGS, one in UTM, and try to lay them on top of each other, it's not going to be perfectly laid, because again, WGS has distortions that UTM doesn't, and UTM for a local situation is more accurate.
Yeah, the difference line in the cell, the primary and the equator for the bottom.
So yes and no, right? So for WGS, the main center of reference is going to be the meridian and the equator. For UTM, even though that's still used to guide the zones, but each zone then has its own center of reference to make the distortions within that zone like to a minimum.
Like the numbers in project and map from this investment is coming from in the geographic is coming from the meridian and the equation.
Right.
In the project, like distance is like 200.
Yeah, so the distance is going to be based within that zone. Yeah. Yeah. All right.
These zones how do you manage? If it's possible, like when you're doing a study where you're calling more than 3 UTM zones, how would you manage the differences?
So whenever you specify within the geographic information system software, whenever you specify the zone, because you have to tell the zone, I cannot just say UTM, I have to say UTM zone X north, right? I have to say that. So whenever you specify that, that information is already accounted for behind the scenes, right? So you don't have to worry about it. Of course, like if you're working with data that is across a large region, especially if it goes across multiple UTM zones, then it's probably easier and best to work with WGS, because then you don't have to be thinking about those differences. But making sure that we use UTM is more important when you're working at a field level. We're doing interpolation, for example, because then you know that the locations are more accurate for that field, right? Good questions. All right, so I just want to give you here a quick reference for these two different coordinate reference systems. So I don't know if you heard about this, but whenever we specify the coordinate reference system that we want to use, it's normally like a lot of like a string, very long string of containing information about that specific coordinate reference system. And it gets very, very complicated to say, this is exactly the one I want to use. So someone at some point came up with the concept of the PSG code. So PSG code is basically a code that you just tell it, like, I want to use the PSG 4326, and the software behind it knows that that is WGS 84. So if you click on this, this is a link. Let me see if I can click on this just to show you. So if I click here, it takes me to the website reference for this. And let's see. So this is all the different ways that we can specify to any GIS software that this is the WGS 84. But like this is something that maybe you would have to copy and paste into R to say this is exactly what you want. And using the EPSG number kind of helps you to not have to copy this entire list of data, and just give it a number and say this is the EPSG I want to use. So that's what EPSG helps us with. It's just like a shortcut to refer to a given coordinate reference system. And again, this works across any GIS software, including R. So the EPSG for WGS 84 is 4326. We're going to be using a lot this number in class. And the UTM N8083 Zone 17 North, again for Georgia, is 6346.
We don't use body placement or only number?
So say that again.
We're gonna use one equation, like,
No, so I mean, depends on the function that we're gonna use, but so some function is gonna be like CRS equals 62346, if you want to specify that, yeah. But just the number itself is what I'm trying to make a point. All right, so we have a quiz. First time we have a quiz before the end of the class. So here's what I want to ask you. So we see here, there's there's a map. I don't want to talk a lot about it because we can tell more about it once you submit your answers. But I want you to look very closely here and list to me each geospatial data layer that you see in this map. And you can just give it a descriptive name, like, because if there's no name here, you can say, whatever you want to call the given layer, or give it a color, or describe it somehow so I know what you're referring to. And tell me if whatever layer you're seeing, if that is a vector or a raster. And as a tip, look closely because there are more than two. So I'm going to give you here 5 minutes. So 9:45. Sorry, what's that? So I want you to look at this map and tell me what are the geospatial layers that you can see here, and tell me like X, Y, Z, W, and tell me for each one if it is a vector or a raster. Does that make sense? So send me your answers, or send me your answer to my email. And so this is a quiz, so I want you to do that in class. I'm going to give you till 9:50, so now we have 4 minutes. And your email to me is also going to be accounted as your attendance. So
Dr. Vasquez,
yes.
I got looking on GitHub this morning, and I noticed that you posted an attendance issue for Wednesday, and I never saw it. I don't think anyone else did. I didn't know what you wanted us to do about that.
Yeah, I mean, so I created that, but I think Dr. Lacerda forgot to mention to you all. So I just disregarded that. I'm going to give presents to everyone because I can't really know who was and who wasn't.
Yes, sir. I was just making sure on that.
Yeah, so I mean, that one you don't have to worry about, but yeah, this one definitely, send me your email with your answers, with your answer, and that will also count as today's attendance. And if anyone has any questions about the quiz, let me know. We can talk more about it. All right, we are at 9:50. I just want to give maybe another minute for y'all to wrap up. All right, so there's still a lot of you missing to send me the email. Don't forget to send the email.
Sorry, so when you say this, what do you mean?
Just, you know, whatever you can call it, so I know what you're referring to. So like, you know, I don't know, layer with the green and reds, or I don't know, something that I know what you're talking about. All right, everyone, we have to keep going. It's okay. I mean, don't overthink it. You know, I just really want to see how your train of thought is going on here. All right, I don't think I received from all of you, but I have to keep going here so the class continues. Make sure that you submitted at least before this class ends. And I would just want to tell you here quickly, I'm going to give you the answer right now. So I will look into your answer, what you submitted afterwards. But before I do that, I just want to make sure you understand what's going on. So this is a UAV imagery that I use for my research to extract vegetation indices to create a variable rate nutrient prescription. This is a small plot research. So what we have here is an NDRE map. So that is what you see as far as like the green and red dots in the background. This is kind of confusing, and this is why we really wanted to see how you would interpret this, because that is raster. The thing is that where you see white is because I removed those pixels, meaning that I removed the data from those pixels. The pixels are still there, but I removed them because they were either soil or shadow, and we want to remove them before taking the average of the plot, because we just want the average of the plant pixels and not anything else. So the NDRE map here, which is again the one with the greens and reds, that is raster. And then the black boundaries you see zoom in. The black boundaries are the plot boundaries, right? So that would be a vector, it's a boundary. And then the shaded area is a little bit confusing because it is also a vector, it is a polygon as well. So the black line is a polygon and the inside is also a polygon. However, here, you know, if you ever worked with field research, you know that we don't use the data coming from the outer rows of the plot because of a border effect. So we basically excluded the borders here and only took the average of the NDRE within the shaded areas, which is also a polygon. So we have So the outer polygon here is the plot boundary, and it has no fill. It just has like the line. And the shaded area is also a polygon that has no line, but it has fill. So that's why it can be a little bit confusing. But I just wanted you to have some idea of what's going on here. All right. So we have 5 minutes here to talk a little bit about the USDA National Agricultural Statistics Service, or NASS for short, data. Has anyone here ever used it, heard about it? Okay, I see some people shaking hands, at least in Athens. So this is a very, very rich data source that the USDA puts out. We're going to be calling the USDA NASS data. So lots and lots of really good information about US agriculture, and just some examples. So the types of data we can retrieve from it would be, for example, the planted or harvested area in acres or million acres in a time series. So we have not only for this past year, but we have for a lot of time going, a lot of historical data as well. We can have, besides area, we can also have yield time series and production time series. And for lots of different crops and lots of geographic levels that can go all the way from a county level to the US nation level. So it's really, really rich data set. So the way that the USDA puts this data out for the public to access is through a portal called QuickStats. So the QuickStats portal is what we're going to use to query and download some NASS data. So we're going to, in next class, we're going to be really working with this as a group and with a data set that's shared among all of us. But then on the mini project, I'm going to assign you a specific crop and specific attribute about that crop for you to work individually. So this data again is free and open source. And this is a link. If you click on that link, this will take you to that website. I do want to, let's see here. So I guess maybe we can wrap up class today by actually downloading the data that I want to work with for next class. So at least we get the data downloaded first, and then we can start working with it next Monday. So you need to go to the portal. If you are on your computer and you're following these slides, this is a link. So if you click on that, this is going to take you to this page. In case you are on Zoom, I'm going to paste the link on the chat so you can also see it. But again, the link is in my slides. And it's like quickstats.nass.usda.gov in case you don't have, you're here in Athens and you don't have my presentation pulled up. So there is really, depending on which boxes you start clicking here, different things are going to start appearing. But my goal for us before this class ends, let me just go back to my slides while still having that. So my goal for us is to download some data. So I want to query data for soybeans production in bushels in the state of Georgia at the county level for all years that they may have available. Okay, so how do we do that? So there's lots of different fields. If we go to the browser, these are the selections that we have to make for that to work. So if you go on your site, there's going to be a sector field, you select crops. On the group field, once that refreshes, you select crop, or let me make sure. You select field crops on group. On commodity, we're going to select soybeans. Make sure you're following, you get the data, because I will not share this data myself. We're all individually going to be downloading in our computers. Soybeans, on the category, I want to go down and select production. Zoom out so you can see the whole thing. On the data item panel, we want to select production measured in bushels. we come to the, we can leave domain without selecting anything. On the select location, we want to do at the county level. So click on county.
Data item, please. Section.
Data item is production measured in bushels. Yeah. Yeah, if you look up here that like it's already sort of highlighted what I've been selecting. So at the state, again, we could do this for all states in the US and get data at the county level. This is how powerful this is. It's really, really informative. But we are going to do for Georgia. We don't want to have specific at districts or counties. We want all of them. So we're not going to make a selection there. And then when it comes to year, we want to select all of them. So you see that the latest one was 2021 and the oldest was like 1959. This is crazy, right? To have this type of data going that much back in time. So you can select all of it. If you can, I think if you just like click and pull down is going to do that. On a Mac, if I push Command, it also helps me to do that. Just make sure you have all the years selected. And then you click on Get Data.
You don't have to select census and that thing.
Select what?
Census also the first column.
No, we just left that without any selection. So it creates a table for us. This is the table that we have. So if you weren't able to follow, I do have the instructions on the slides. You should be able to follow afterwards. But what I want you to do is just go here. So I mean, this data has like almost 7,000 rows. So we're going to start talking about some big, well, not big data, but larger than maybe just field data that we worked with the soybean example. So to download it, you can click on that spreadsheet link, and that's basically going to download it to your computer. Right, so it has a very weird name to it. So I want to ask you to see where this was saved to your computer and just rename that to, let me see what I have on my slides. Rename that to soybeans_NASS, and it is a CSV file, so maybe the .csv is already there, but just rename it to soybeans.nas. And then we can stop here today, and we're going to continue next class. And the first thing we're going to do in class is create a new project, new RStudio project, all that. If you're ready, want to go ahead and do it. I have some instructions here. However, again, setting up the project, folder structure, and where you save things is the first step for things to start well. If you do some mistake in that stage, it's going to be difficult to import data and export data as well. So we're going to walk through in next class how to do this, but I have the instructions there. They're pretty self-explanatory if you want to go ahead and try. So this is all that I had today. Thanks, everyone. Let me know if you have any questions.